Picture a thick steel shaft inside a heavy industrial machine, vibrating until it suddenly shears in half. Now picture the digital maintenance dashboard for that same plant. The indicators are all green. The KPIs look perfect. This is a common paradox. On paper, the failure history looks clean. But when a reliability engineer reviews the records to find out why that shaft snapped, the data falls apart. Spare parts cannot be linked to the work orders, and the physical asset that just failed essentially vanishes from the digital record. The immediate reaction is to blame the software or a lack of discipline from the technicians entering the data. Neither of those is the root cause. This is a foundational data architecture problem. In maintenance information management, structure must precede content. Regardless of the software platform, every maintenance management system relies on 5 distinct types of data. These 5 types sit in a strict unidirectional flow. To see how they interact, we are going to build this flow from scratch. If an organization cannot classify a piece of data into one of these 5 specific layers, that data cannot be governed or trusted to drive reliability decisions. We start at the absolute baseline, the moment before any maintenance user even logs in to a new system. The first layer is system configuration data. This is the structural shape of the system itself. It defines the boundaries of the environment, the plant codes, the cost centers, and the user security profiles. It acts as the secure container where assets will live. It rarely changes and is strictly owned by IT. Next, we add master data. This layer represents real physical and logical objects. For example, we create a specific asset in the system, gas compressor GC2201, established as a functional location. This layer requires immediate structural links. We connect the compressor to a bill of materials containing 74 spare parts and attach its required preventive maintenance job plans. Master data changes slowly. Updates require formal management of change approval and must be managed by a dedicated data steward rather than IT. Master data defines what the system believes exists. If an asset lacks a master record, the system is blind to its existence. Having a physical asset in the system is useless if there is no standardized way to describe what happens to it. That brings us to data type 3, work process data. This layer acts as the system's rulebook. It provides standard reference values, cause catalogs, and equipment classification codes. This governed vocabulary forces users to select from controlled lists, preventing them from inventing their own terminology in free text fields. Once the rules are set, we get data type 4, transactional data. This records the live events occurring on the equipment. These are the daily inputs: craft hours logged, parts consumed from inventory, and specific failure modes recorded during repairs. A large plant generates tens of thousands of these records as operations and maintenance teams execute their daily tasks. Every transactional record draws its context from the work process rules and master data objects established upstream. Frontline data entry is a byproduct of the upstream architecture. You cannot fix structural data problems by demanding better work order discipline from technicians. What happens to that massive volume of transactional data once a work order is closed out? It becomes data type 5, historical data. Once data enters this archive, it is immutable and read-only by design. This pristine history enables analytical tools, like a Weibull analysis, to accurately predict failure intervals across an entire fleet of similar assets. Insights extracted from this history flow back to the master data layer, allowing us to optimize parameters, such as extending a preventive maintenance interval based on real-world performance. This archive powers continuous reliability improvement, provided the preceding 4 layers are governed correctly. We now have a running 5-layer directional flow. The most destructive error an organization can make is categorical substitution, using the wrong data type for a specific task. The first failure mode is treating transactional data as master data. This happens when a planner schedules work for a new piece of equipment, but instead of building the master record first, they type the equipment's name directly into a work order description field. Because it bypassed the foundation layer, that asset officially does not exist. It generates no searchable history. To reliability engineers, it is a ghost. The second failure mode is treating master data as work process data. Here, an organization allows local sites to invent their own equipment classification codes inside the master record, ignoring the central rulebook. Enterprise reporting instantly fractures. Benchmarking across sites becomes impossible, and analytical algorithms fail to recognize identical equipment. These dashboard failures stem from structural bypasses rather than simple errors in technician discipline. The third failure mode is treating historical data as editable. This occurs when a user reopens a closed work order and retroactively reclassifies an old failure mode to make current KPIs look better. The moment history is altered, the trend loses integrity. Any reliability decision based on that tampered data is built on sand. A functional system replaces free text fields with governed catalogs and protects historical records by design. Software cannot police itself. To maintain this architecture, an organization must appoint named human data stewards to own the master and work process layers. If you respect the directional flow, keep the 5 data types strictly separated, and assign clear ownership, your maintenance program becomes predictable. Blur those lines, and you will spend years cleaning up avoidable mistakes.